Hey everyone, and welcome to my first YouTube video. Today, in this video, I'll be covering the first chapter of the general chemistry section of the MCAT, which is atomic structure. So let's just dive right in. So first off, we have the atom here. And in this diagram, we see two main components. We have the atomic nucleus, which contains neutrons, which have a zero charge, or neutral charge, and protons, which have a +1 charge. And then surrounding the nucleus, we have this electron orbital, or you could have multiple orbitals depending on the element. And these orbitals are regions where we can find negatively charged electrons, which have a 1- charge each. And so few important points are that, first off, the mass of a proton is about 1 atomic mass unit. That's what this abbreviation is for. The mass of a neutron is slightly greater than that of a proton, so slightly greater than 1 AMU. And the mass of an electron is an almost negligible 1/2000 AMUs. So there's two important things we need to know for element notation, and that's atomic or Z number, which describes the number of protons in an element or ion, and the mass/A number, which describes the number of neutrons and protons summed together. And so these are the two ways we can notate elements. We can have the A number in the top left with the Z number on the bottom left of the element, or we could have the Z number above the element written with the A number below the element. So if I tell you there's an atom with a Z number of 9 and an A number of 19, could you tell me how many neutrons are in this atom? So we know that the Z number tells us how many protons we have. So we have 9. And we know the A number is the sum of the neutrons and protons. So 19 minus 9 would leave us with just neutrons, so that's 10. Now, if there's elements that have the same number of protons, but different amount of neutrons, we call those isotopes. So in other words, they have the same Z number, but different A numbers. We also have to know what atomic mass is. So atomic mass is just the A number, so the number of protons and neutrons combined. And atomic weight, although it sounds similar to atomic mass, you shouldn't get these confused. Atomic weight is the weighted average of isotopes for an element. So for example, we have this element here, we'll just call it X. And element X has 3 isotopes, M, N, and P. The isotope M has a Z number of 26 and an A number of 56. The isotope N has an A number of 58, and the P isotope has an A number of 60. And so we're told that the atomic weight, so the weighted average of all these isotopes, is 58.4 atomic mass units. So we're trying to determine the percent abundance of isotope P. So how can we do that? Well, there's a general way to approach these questions, and what you do is you multiply the percentage of each isotope to its atomic mass units as a ratio. So 0.2 would be 20%. You'd multiply that by 56 AMU plus, and you repeat this for every single isotope and equal it to the atomic weight, which is 58.4. So here, if we go back here, we know there's 40%, sorry about that, 40%, that's 0.4 as a ratio times 58. And then finally, here, let me just move this equation a bit more to the right. so we can have more space. Finally, the last isotope has an atomic mass of 60, but we don't know what the percent abundance is. So we're just going to multiply the atomic mass, 60, by x, which is our ratio that we want to determine. Now what we can do is we could just, and as you guys probably know, you're not going to have a calculator on the MCAT exam, so we're going to have to do this manually, and it's not too difficult. We can rewrite 0.2 as 2 times 10 to the negative 1, all that multiplied by 56, plus, in 0.4 we can do the same thing, so that's 4 times 10 to the negative 1 times 58, plus, and this stays the same, just put 60x, equals 58.4. Okay, so 2 times 56, that's 112, times 0.1, which is this 10 to the negative 1, that's going to be 11.2, plus, and for the second term, we have 4 times 58. 2 times 58 is 116. You multiply that by another 2, that's 232 times 10 to the negative 1, which I'll just erase this and write the more simplified version, which is 23.2, plus 60x equals 58.4. And these are all atomic mass units. So now we can simplify this. 11.2 plus 23.2 is 34.4 plus 60x equals 58.4. Now if you subtract both sides by 34.4, we get 60x equals, now how do we do this? We can say this is 50 plus 8.4 minus 30 minus 4.4. So we can write this as 60x. 50 minus 30 is 20. 8.4 minus 4.4 is simply 4 plus 4. So we have 60x equals 24. X equals 24 divided by 60. And that ratio gives us 0.4 because these are both, the numerator is a multiple of 6, so 4. The denominator is also a multiple of 6, so 10 times 6. That gives us 0.4. So the percent abundance of the P isotope is 40%. Oh, and just before we go on, I forgot to mention that atoms that gain electrons become anions, and atoms that lose them become cations. Okay, so let's move on to theories of the atomic model. So first off, there's Rutherford's theory, which is basically an atom with a positively charged nucleus in the center with negatively charged electrons surrounding it. And he discovered this using the gold foil experiment, where he shot positively charged alpha particles from a source of alpha particles like radioactive decaying element. And these alpha particles were shot at a gold foil. And some of these particles hit the back of a film that was placed behind the gold foil. But some of them reflected, like these two. And the only explanation for that was that there must have been a positively charged component of the atom, or the atoms that make up this gold foil. And the rationale was that like charges repel each other. Then he concluded that there must be a positively charged nucleus in each atom. Another important figure was Planck. He contributed to the quantum mechanical model of the atom, and he came up with the idea that electromagnetic radiation is energy which is emitted as discrete quantities, or quanta. And he came up with this equation, E equals hf, which is called the Planck relation. And this relates energy to the Planck constant, which is h, and the frequency of the electromagnetic radiation, which is f. And with Planck's ideas of electromagnetic radiation, specifically how they're released as quanta, or discrete packets of energy, Bohr, which is another scientist, came up with his own atomic model, where we have a positively charged atomic nucleus surrounded by shells, or energy levels, which contain negatively charged electrons. So you can see here there's first energy shell, second energy shell, and we denote this with the letter N. So N equals 1 denotes the first shell, N equals 2 second, N equals 6 would be the sixth shell, so on and so forth. And with this information, we also have another formula, which you don't necessarily have to memorize for the MCAT, but it's good to know the general concept. So we have energy equaling to the negative constant, which we call the Rydberg constant, divided by n squared, which is energy levels, or energy shells squared. And the important thing to notice here is that energy is directly proportional to energy shells. So as the energy shells increase for the electron, so say there's an electron in the seventh energy shell, that's going to have more energy than an electron in the first energy shell, or the second or third. And that's because as n increases, as n squared, this denominator term increases, this entire term becomes less and less negative, meaning the electron is going to end up having more and more energy. There are some more terms we need to know regarding the quantum mechanical model of the atom, and that's ground state and excited state. And these terms are used to describe the nature of an electron. So ground state basically means lowest possible energy. So if there's an electron initially in the n equals 1 energy level, then it's in its ground state. But if this electron jumps to an n equals 2 energy level, then it becomes excited. And that's when it absorbs a photon. And if this photon is emitted, again, from the electron, then it's going to jump back from n equals 2 to n equals 1 and become ground state again. And it's important to mention that this photon, which is getting the electron from n equals 1 to n equals 2, can have a very different effect than other photons. Another photon could come, get absorbed, and make this electron jump from n equals 1 to, for example, n equals 3, or n equals 4, or 5. It all depends on the energy of the photon. And so here's the formula you need to know, or rather understand, and that's E equals hc. This is Planck's constant, as we covered earlier, and c is 3 times 10 to the 8 meters per second, and this term here in the denominator is the wavelength of the photon. So you don't really need to memorize or do any calculations with this formula. What you really need to get out of this is that energy is inversely proportional to the wavelength of the photon. And so what this means is that if the wavelength decreases, this bottom term becomes smaller and the entire term becomes bigger. So bigger if this decreases, if the wavelength decreases, and vice versa. So it becomes smaller if the wavelength increases because the entire term becomes smaller. Since the numerator, of course, stays the same and it just remains at 1. And we also know that we know that wavelength is equal to 1 over frequency of the photon. Or we can say frequency equals 1 over wavelength. So what this means now is that energy is directly proportional to frequency. So as the frequency of the photon increases, the energy also increases. That's pretty much all you need to know. I'd mentioned that there are different photons that can be absorbed, and depending on the energies of those photons, there's different jumps in energy levels. And here's some terms you might need to remember for that. So jumps from n equals 1 to any energy level are called Lyman series. So an electron going from here, n equals 1, to n equals 3, this would be considered the Lyman series. There's also Balmer series where electrons jump from n equals 2 energy level to higher energy levels. So say n equals 2 to n equals 3, or n equals 2 to n equals 4. And by the way, there can also be a drop in energy levels. So, it's a transition. So you can have an electron here in n equals 4, emitting a photon that has a specific wavelength that gets it to n equals 2. And then there's also the Paschen series, which gets you from n equals 3 to higher energy levels. And that's denoted by m, by the way. So yeah, n equals 3 to n equals 4, and I didn't draw n equals 5, but it continues. So we can have n equals 3 going to n equals 4. This photon's absorbed into the electron. That causes the jump, or the photon can be emitted and the electron can go back down to n equals 3 from higher energy levels. So one formula that relates to the series is this right here. E equals the Rydberg constant multiplied by 1 over m squared, m being a higher energy level or higher energy shell, minus 1 over n squared, which is the lower energy shell or energy level. And what's basically happening here is, well, let's say, for example, we have an m, an energy level for m as 3. So then you have 1 over 9 minus 1 over, and let's say the lower energy level is 2. So we have 1 over 2 squared, which is 1 over 4. This value is going to end up being negative. Here, let me just move this around. This value is going to be negative because you have a smaller value subtracted by a bigger value. And essentially what this means is that the energy of the electron decreases as it goes from a higher energy shell to a lower energy shell. So if m is 3 and n equals 2, then we're going to have a loss of energy. And so this means that energy, as I've written here, is lost in these transitions. And this is, of course, from higher to lower energy levels. If we're going from lower energy levels to higher energy levels, there's going to be an increase in energy. Okay, so I know I've mentioned the quantum mechanical model a couple of times to refer to other theories, but now I'm going to go in depth and explain what it really is. So it describes atoms as containing a nucleus surrounded by clouds of electrons, and these clouds of electrons are called orbitals. And so there's a few principles you need to know regarding the quantum mechanical model, and the first one is the Heisenberg uncertainty principle, which says that we can't know the position and momentum of an electron simultaneously. We can know the position very well if we assume it has zero momentum, but then we won't actually know what the momentum is. And vice versa, if we know what the momentum is, and given the electron is moving and it actually has a momentum, we won't be able to get a specific position for that electron. So that's basically the Heisenberg uncertainty principle. And then there's quantum numbers for these electron orbitals or clouds. So to describe electrons, there's the principal or n number, and this describes the energy level or shell that the electron resides in. So if we go back to our Bohr model here, if an electron is here and the n equals 1, well, yeah, n equals 1. We already kind of talked about this, so this isn't really new information. And then if it's in the second energy shell, it's n equals 2, so on and so forth. Okay, and there's also the L quantum number, or the azimuthal quantum number, which describes the shape of subshells, and it's numbered n minus 1. So whatever your principal quantum number is, your L number can be n minus 1 all the way down to 0. So, and if we go down here, we have, so yeah, we usually have 3 quantum L numbers. There's 0, 1, 2, and 3 that we need to worry about, and that's S, P, D, F. So 0 is S, P is 1, D is 2, and 3 is F subshells. And the S subshell resembles spheres, and these are an area where electrons can reside in. And the P subshells look like dumbbells, and the D subshells, although you probably won't have to memorize, looks like somewhat of a clover. And then the F, there's different shapes and just way too many to memorize, so don't worry about that. But so these are the 4 L numbers and 4 different types of subshells. And if we go down here into our periodic table, we'll see that the first and second row elements, which have valence electrons in these rows, will have S subshells, including helium. Helium's an exception because you usually write it on the right side of the periodic table since it's a noble gas, but this is also a 1s subshell here. Then we have rows 3 to 12, which are transition metals, and these have electrons with D subshells. And rows 13 to 18, except for helium, have P orbitals or subshells. And we also have our F block, though you don't need to know what the shape of those orbitals or subshells are. We also have the ML, or magnetic quantum number, which describes the orientation of orbitals within a subshell. And this value is numbered from negative L to 0 all the way up to positive L. So if we're looking at a D subshell right here, we know that D is L equals 2. That's the azimuthal quantum number. And so we would have negative 2 orientation, negative 1, 0, 1, and 2 orientation. And if you're trying to number or find electron configurations on the periodic table, for the D block, we'd start numbering from negative to positive for the ML quantum number. So we said there was negative 2 to positive 2 orientation, so we'd go here, and this would be negative 2, negative 1, 0, 1, 2. And then you repeat that one more time, because there are 2 electrons for each orbital. This would be negative 1, 0, 1, and 2. And you could do that for P as well, and S, and the rules are the same. And finally, we have the MS, or spin quantum number, and this describes the spin orientations of the electrons that are paired in an orbital. And so the value we could have for an electron for the spin orientation is -1/2 or +1/2. If we want to figure out electronic configuration, we have to know a few principles. So firstly, there's the Aufbau principle, which states that energy shells are filled from the low ones first to the higher energy shells. And they are filled in this order. So starting from 1s, going to 2s, 2p to 3s, 3p to 4s, 3d to 4p to 5s, 4d to 5p to 6s, 4f to 5d to 6p to 7s, and so on. The Pauli exclusion principle states that paired electrons must have opposite spins. In other words, they can't have the exact same quantum number or set of quantum numbers, because if they had the same spin and they were paired, they'd have both the same principal quantum number, same L number, same ML, same MS, because they would both have positive or negative 1/2 spins. Another rule is Hund's rule, and Hund's rule states that orbitals with the same energy, we call these degenerate orbitals. So orbitals that have the same energy are singly filled first before being paired with electrons. So if we go back to our periodic table, orbitals in the 2p subshell, so this orbital here, this one here, all of these are degenerate because they have the same principal quantum number, which is n equals 2, and they have the same subshell. So these are degenerate. And so what happens here is that the orbitals, the three we have, -1, 0, and 1, get singly filled with a positive half-spin electron, each one of them, before being doubly filled with the negative half-spin electron. Okay, so let's do some examples to better grasp quantum numbers. So let's find the electron configuration of vanadium, which has a Z number of 23, and since it's an atom, it's going to have the same number of electrons, so we have 23 E minus, 23 electrons. Vanadium is right here on the periodic table, and so we want to find the electron configuration. So we first start by making use of the Aufbau principle. So we start at the 1s orbital, and so we know 1s has 1 and 2 electrons. So there's 1 goes here, 1 goes here. We have 1s2. We're going to use the telescopic notation. 1s2, the superscript denotes the number of electrons in that orbital. And then we fill the 2s orbital with, again, 2 electrons, same as the 1s. So we go here, and we have 2s2. And then the next orbital we fill is 2p. 2p is right here. And 2p is going to contain 1, 2, 3, 4, 5, 6 electrons. So we go back down here. 2p6. And then if we look back at our diagram here, so we can see that we're filling the 3s orbital now. And so we go here. That again only has 2 electrons, like 1s and 2s. Go here, 3s2. And then we don't fill the 3d subshell, but we will fill the 3p because we're just following the diagram here for the FBAT principle. We just did 3s, now we're going to fill 3p. 3p 6, and then 4s, because that's the next subshell we have, and that's going to be 4s2. And now we're going to fill the 3d subshell, because we just did 4s, now we're going to 3d. And 3d is going to have 1 and 2 electrons, so that's just going to be 3d2. And this is our electronic configuration for vanadium. We can also do the shorthand notation, which starts with the highest noble gas before the last row we're working with. So that would be this noble gas right here, which is argon. So the way we denote this is we write AR and then we continue as usual. So we assume we just did the 3p orbital and we filled that and everything before that, and then we go on to 4s, and then it's the same thing, 4s2 and then 3d2. Okay, for the second example, we have to find the electron that satisfies all 4 of these quantum numbers. So let's start with our options when we consider the principal quantum number n equals 5. So if we go to our periodic table, if n equals 5, we could have electrons in the 5s subshell or the 5d subshell or 5p, as well as 5f. We must also take that into consideration. So our options are narrowed down, but we still have a lot to go with. So now let's look at L equals 2. So what L equals 2 means is that if we look again at our options, we have 0, 1, 2, and 3 for our possible L numbers. And 0 is S, 1 is P, 2 is D. So we are working with a D subshell. So now we have narrowed our options quite a bit. Let me erase this. No 5p, no 5f. We're just working with 5d subshell. And we also know that the ML quantum number is equal to 0. And this means that we have -2, -1, 0, 1, 2 orientations, and out of all of these, we're just working with 0 orientations. But since we have 2 electrons in each orbital for our subshell, we're going to have to consider the MS value as well. But first, let's look at ML. So we're working with 0, so if we go back up here, we start numbering from negative to positive, so -2, -1, 0, 1, 2. Here, just squeeze that in right there. And then since we have 2 electrons, we do that again, -2, -1, 0, 1, 2. So our electron could be right here on the periodic table, or it could be right here. So again, we're narrowing our options. We have that. And now let's consider the MS, or the spin quantum number. So we first fill degenerate orbitals with negative spin electrons, and then we pair them with the opposite spin electrons, which are positive 1/2. Or sorry, other way around. So we fill them first with positive 1/2, then negative 1/2 spin electrons. To be honest, it really doesn't matter which way or which spin you start with. But usually you're going to be writing the positive number first and then filling the orbitals, pairing them then with the negative spins. So we first start with positive spin. We have positive 1 over 2 here, positive 1 over 2, positive 1 over 2. And then we go positive 1 over 2, positive 1 over 2. And those are all our 5 orbitals that have just been filled with positive spin electrons. And now, since they're singly filled and they're all degenerate orbitals, all filled, now we pair them with the opposite spin. So negative 1 over 2, negative 1 over 2, negative 1 over 2, negative 1 over 2, and negative 1 over 2. And now they're all paired. So let's see what our options are. The first option we have says that our electron has a positive half spin, which is just wrong because ours has a negative half spin. So we can conclude that our electron is right here on the periodic table. Okay, and let's look at our last example. We have this anion iodide, and we want to determine the electronic configuration of this ion's valence electrons. So one thing you have to know is that valence electrons are in the highest principal quantum number, highest n number. So with that information, let's look at our periodic table and try to figure this question out. So we know iodine is here, and we know that it is an ion, so it's going to have a noble gas configuration. So what we're looking at here is, okay, if it has a noble gas configuration, it's going to fill this subshell fully. It initially only filled it with 5 electrons, 1, 2, 3, 4, 5. But since it's an anion and gained an electron, it's also going to fill this last orbital. So we're going to have a full 5p orbital, or subshell, sorry. And we're also going to have full 4d, full 5s, and everything above that, all of these, are also going to be full, assuming all electrons are in the ground state. So, with that in mind, now let's look at the valence electrons. So we said that valence electrons occupy the highest energy shell. And the highest energy shell in our case, for iodine, or iodide, is 5. So we're going to be looking at this subshell. We're also going to be looking at the 5s subshell, but not the 4d subshell. And why is that? Well, that's because it has a lower quantum n principal number. And yeah, so do not get that confused. Just because they're in the same row doesn't mean that they're all valence electrons. So to write the electronic configuration for the valence electrons, we're just going to have a full 5s subshell as well as a full 5p. So as we know, 5s gets filled first because of the Aufbau principle. The 5s is here, and then 5p comes later. So we're going to have 5s2, and we're going to have 5p, and we know that p has 6 electrons, 1, 2, 3, 4, 5, 6. It has 6 because it's an anion and gained an electron. 5p6, and that's the electronic configuration of the valence electrons for this iodide ion. Okay, and the last thing we need to know for this chapter is magnetism. Unpaired electrons and orbitals make an atom or ion paramagnetic. And if there are only paired electrons and orbitals of an atom or ion, that makes it diamagnetic. So let's go over some examples. So for our first example, we're going to determine the magnetism of chloride. So we're going to have to know two things. We're going to have to be able to determine the electron configuration of chloride, as well as being able to do the orbital diagram for this ion. So the orbital diagram is similar to the telescopic notation of electronic configuration, except you're drawing the electrons being occupied in subshells like this with positive spin, negative spin electrons. And yeah, so you'd have your orbitals here for 2p, for example, and so on and so forth. So let's take a look at chloride. So chloride is going to occupy a full 3p subshell with electrons, and everything before that's also going to be fully occupied with electrons. So we're just going to start with the valence shell, which is going to be the n equals 3 subshells, so these two, because we know everything before that's going to be full. So we're just going to look at the 3s. We know that's full, and we're going to also look at 3p6. That's also full because it's an anion, and it gained an electron to obtain a noble gas configuration. So 3s2, we're going to start here, and this is going to be paired with electrons. Since 3s and 3p are not degenerate, this gets doubly filled before 3p gets singly filled and doubly filled. And then we go to 3p. So we know that there's going to be 6 electrons in total for the subshell, and we know there's 3 orbitals. We're going to singly fill these first with positive spin electrons, and then doubly with negative spin electrons. And as we can see here, every orbital has paired electrons. There are no orbitals with unpaired electrons, so this is a diamagnetic ion. So chloride is diamagnetic, meaning it's not going to stick to a magnet. For our next example, we have calcium cation. And if we go back to our periodic table, we know that calcium is right here. And since we know that the shells below the valence shell, which is the 4s, are all going to be fully filled and paired, we're just going to look at the final valence shell, which is the 4s. So this is a pretty simple example. We're just going to have 4s, and since it's a cation with a positive 1 charge, we know that there's going to be only 1 electron in this orbital. And since this electron is unpaired, we know that it is paramagnetic, so this ion is going to stick to a magnet. Okay, and that's it for this video. I hope you guys enjoyed, and I hope that you found this to be helpful. And if you did, please consider subscribing or leaving a like or even a comment expressing how helpful the video was or if there's anything I missed. And I'll see you guys later.